Okay, so we're going to take a look at drawing electron dot diagrams today. These are known as Lewis structures. So you're going to have the symbol for an element surrounded by dots, which represent the valence electrons. And has anybody done these before? Okay, so we're going to take a look at neutral atoms first, and then I'll move into ions or ionic compounds, and then we'll spend the rest of class doing covalent compounds. So Gilbert Lewis is the person that came up with this concept, and when we are drawing the Lewis structures for neutral atoms, you're going to have the symbol for the element with the number of valence electrons represented as dots. Some teachers will teach you that there's a formal rule to place the dots. Technically there isn't. So here this is showing you that elements in group 1A or group 1 would have one dot on them because they have one valence electron. And then elements in 2A would have two dots because they have two valence electrons. And then it proceeds from there. 3A, 4A, 5A, 6A, 7A, 8A. All of those elements have the corresponding dots that go with their valence electrons. The only one that is an exception to being in 8A is helium, because helium only has two valence electrons, so it would only have two dots on it. Okay? You will have a maximum of 8 dots. You can have 2 on each side. Okay? So when we move out from there, and we take a look at ions. If we're looking at sodium chloride, which is NaCl, sodium is my metal, chlorine is my nonmetal. In a previous section, we looked at sodium giving its one valence electron over to chlorine during ionic bond formation. Okay, so individually, here's sodium with its one valence electron and chlorine with its 7. So what happens is the metal will give its valence electrons to the nonmetal because it reveals the octet that the metal has underneath. The metal will form a +1 charge, and then the nonmetal, now that it has 8, will form a -1 charge. Now, the metals and the nonmetals are always drawn the same way when they're in ion form. So let me explain. You will have a metal with its usual charge in the upper right-hand corner in brackets. You will never have dots on it. It will look like this. Okay, and that's because all the metals will give away their valence electrons to the nonmetals. But the nonmetals will be with 8 dots in a bracket, and the charge will be in the upper right-hand corner. Okay? God bless you. Depending upon whether you have more of the metal or the non-metal ions in a chemical formula, you may see them alternate the structures to make them look symmetrical. You may also see a subscript written to indicate that there's more than one of them. Okay, both of them are okay. One is just sometimes easier to draw than the other one, depending upon how many you have. Okay, can I move on from here? Okay, so let's take a look at a couple of things here. Let's take a look at number 2. They want us to write the Lewis structures for these neutral atoms and ions. Okay, barium is in group 2A. How many dots would barium have on it? 2, yeah. It's 2 valence electrons. We have the aluminum ion. Is aluminum a metal or a non-metal? It's a metal. So since this is a metal ion, you would put the symbol in a bracket with its charge in the upper right-hand corner, and you're done. Okay? Bismuth is where? Is bismuth one of our metalloids? No? I don't think so, is it? No, it's just a neutral metal, but it is in group 5A. So how many dots will it have? Yeah. 1, 2, 3, 4, 5. Doesn't matter where you put them as long as you have a max of 2 dots on each side. So like top, bottom, left, or right. Okay. And then I-1, this is a non-metal ion. So for the non-metal ions, you have to have 8 dots on it. It goes in a bracket with its usual charge on the outside. Okay, you get the idea. I don't think we need to do any more. Agreed? It's easy. Okay, so let's take a look at the next page. This is where I'm going to be spending the rest of my time. So this is where we start drawing Lewis structures for molecules. So that means these are going to be non-metal compounds. I'm going to be like outlining the steps out loud. So we're going to first start with the molecule Cl2. Okay. When you draw Lewis structures for molecules, you want to make it look symmetrical. So you want to put the atoms next to each other or surround them in such a way so it kind of looks symmetrical. And what you want to do is connect them with a line, which represents a single bond. So this single bond will account for 2 of our valence electrons. Okay? You know that chlorine is in group 7A. So since I have 2 chlorines in 7A, 2 times 7 would give me 14 valence electrons total. I just used 2 when I drew in this single bond. So that means I'm going to go ahead and subtract 2 from my total, which leaves me with 12. Does this make sense what I just did? Okay. So since I've got 12 remaining, put them on the chlorines in pairs. They always go on in pairs. You never separate them. So I have 2, 4, 6, 8, 10, 12. Okay. You're never going to put them over here like where you already drew your bond. And then what we're trying to do is get every atom to be surrounded by 8 electrons so that we can satisfy the octet rule. Okay? Okay, now, a couple of terms. Let's talk about lone pairs and bonding pairs. So, lone pairs of electrons, which are often abbreviated as LP. These are the pairs of electrons that are not participating in bonding. So, here in this example, I've got 1, 2, 3, 4, 5, 6 lone pairs. Okay, but that bond in the middle, which has a pair of electrons in it, that would be a bonding pair. So a bonding pair would be abbreviated BP, and I have 1 of them. It's that one in the middle. We good so far? Okay, let's draw some more then. Let's take a look at NCl3. So let's go to the next page. Okay, in order to make this look symmetrical, put the nitrogen in the middle, put a chlorine on either side, and then the third chlorine could go above or below the nitrogen, it doesn't matter. Connect them with lines. Those lines represent single bonds. Nitrogen is in 5A, chlorine is in 7A. So I have 5 valence electrons for nitrogen plus 3 chlorines in 7A. So this is 21 plus 5. So we have 26 electrons to work with. When I drew in my single bonds, I used 6 electrons total because there's 2 in each bond. So I need to subtract the 6 electrons that were drawn, and that leaves me with 20. I'm going to put the remaining 20 electrons in pairs on each atom. So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, and then the last pair will go on the top of nitrogen, 20. Okay, each atom is surrounded by 8 electrons, so everybody is happy. Now, in terms of lone pairs and bonding pairs, I have 3 bonding pairs because I have 3 bonds. And then for lone pairs, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We good? Yeah? Okay, cool. Then let's go over some of the guidelines, and then we'll go over some of the exceptions. Sometimes you will have a central atom that can accommodate more than 8 electrons, and this is called an expanded octet. You know you have this if you end up having a ton of electrons left over. So if you have an element in the 3rd period or higher, since they have access to d orbitals, they have the ability to accept more than 8. Okay, so this would be something like phosphorus, which is in the 3rd period, or sulfur, or you could have arsenic or iodine or bromine, okay, just as examples. So the other thing is there are exceptions to the octet rule. I will be marking those as we move throughout, but I'd like you to know that beryllium and boron are exceptions. Beryllium only wants to have 2 bonds coming off of it at any time, and that's because it only has 2 electrons to share. Boron wants to have 3 bonds because it only has 3 electrons to share. They also say the same thing about aluminum, but I really don't think you're going to have that ever in this class. Okay, so I wouldn't worry so much about that. The other exception would be hydrogen. Hydrogen only has 1 valence electron to share, so hydrogen only wants a single bond coming off of itself at any time, okay? Okay. All right, next page. Let's take a look at the practice problems here. Did I skip a page or are we good? We're good? Okay, so what I'd like you to do with the person sitting next to you is, oops, I want you to draw carbon tetrachloride, ammonia, and boron trichloride, and let's see what you guys come up with. Okay, did you get something that looked like that? Any questions for me? Yeah.
If there was like an odd number of like
You
electrons, would it
will
just
never have that.
oh okay.
Not in this class. Okay?
Okay. Or what if there's like not enough for it to have like a pair?
That will never happen.
Okay.
Yeah.